Hello, uh, myself Dr. Rajesh Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus. The subject that I teach in this semester for EC branch students of fifth semester, digital communication, and the topic that I discuss today is review of sampling theorem. You know, uh, normally, or you must say naturally, the signal that we have is an analog signal, right? So normally the signal that we deal in communication is a analog signal, and when we deal signal in digital communication, we need a digital signal. But normally we have an analog signal, right? So analog signal is to be converted into digital signal, right? So normally we have an analog signal in communication, but if you want to send a signal, digital signal, then you have to convert that analog signal into a digital signal. So digital signal is superior as compared to analog signal because it is more robust to noise, because the effect of noise is minimum in digital signals and can easily be recovered and corrected and amplified. So these are some advantage of digital signal over analog signal. So in digital communication, we deal with digital signals, but normally the information we have in the form of some electrical signal, and that electrical signal has a nature of analog signal. We have to convert this analog signal into a digital signal, and we already talking about the advantage of digital signal over analog signal because of less possibility of noise in digital communication, digital signal as compared to analog signal. So for this particular reason, the tendency today is to change an analog signal to digital signal, right? When we say digital signal, actually it is a digital data of 0 and 1 bit. So so normally we have a analog signal. What we have to do, we have to take the samples of continuous time signal. That continuous time signal is the analog signal, right? So when we are talking about analog signal, actually we are talking about continuous time signals that has defined at every moment of time. Now what we do, we take some samples of this analog signals, right? Some samples of analog signal according to sampling theorem, and convert these samples into a discrete pulses, right? And then once we have a discrete pulses, then we have to send these discrete pulses uh, to a destination over some physical transmission medium, right? This is the process. The process start with the in analog signal. Second is take the samples from the analog signals, then convert these samples into a discrete pulses and send these discrete pulses over a transmission medium. So as far as the sampling theorem is concerned, sampling is the process of taking samples of analog signal at a given interval of time. Only samples are being transmitted. Means, as far as analog signal is concerned, we have to take some samples of analog signals, right? So we just send the samples of a analog signal, not complete all the samples of a analog signal, right? So if there are thousands of samples contained in a particular analog signal, we have to take some hundreds of samples from that thousands of samples, and we have to send these sample at a given interval of time, right? So if we take the samples from we take the samples from this particular analog signals, so samples represent this whole analog signal. So it is not necessary to send the whole analog signal. In digital communication, we always send the samples of analog signal. So if sufficient samples are sent and sampling theorem are met, the original signal can be reconstructed at the receiver. Means if you send a sufficient amount of samples by by taking this sampling theorem in your mind, by obey the rule of sampling theorem, then these samples first represent the whole analog signal. Not only that, when these samples are reached at the receiver side, we can construct or reconstruct the whole analog signal at the receiver side with the help of these samples that represent an analog signal. So sampling theorem states that if the sampling rate in any pulse modulation system exceeds twice the maximum information signal frequency, the original signal can be reconstructed in the receiver with the minimum distortion. The meaning is that if you have an analog signal, if you take the samples according to the sampling theorem, actually in analog signal there are so many frequency components present in that signal. When we say so many frequency component, means some components are high, some components are low. So if we consider the highest frequency component present in the analog signal, we always consider that frequency, right? So whenever we consider the frequency component of analog signal, we take that particular component that have the highest frequency, right? So if you take the samples according to sampling theorem, we must take a sample twice the maximum frequency component in that analog signal, right? So if you take this particular rule in your mind and just take the samples fs represent a sampling frequency and fmax represent the maximum frequency component present in the analog signal. So if your sampling frequency rate is twice greater than or equal to twice fm, then everything is okay. So if you take the samples according to twice fmax, then we say that you have to take the samples according to the rule. So when fs is exactly equals to twice fmax, then we call this particular condition is a Nyquist condition, right? So the minimum frequency, sometimes we say what is the minimum sampling that we take. The minimum sampling is called as a Nyquist state, which is equal to twice fmx. So we always take the samples greater than or equal to twice fm, where fmax or fm is the maximum frequency component present in the analog signal. Two types of samplings are there: natural sampling and flat top sampling. We will discuss that. So look at this particular picture. In this picture, we have analog signal. Second picture shows that we take the samples, convert the samples into pulses. So we have these pulses. So we convert analog signal into some samples convert into pulses. So these pulses are the representative sampling signal, right? And the maximum frequency component is fm in this analog signal. So we have to take twice fm and twice kHz. So sampling fs should be greater than or equal to twice fm, and we obey this particular rule because the sampling signal frequency fs is 8 kHz, which is greater than twice fm, right? So everything is to be okay in this particular picture. Now look at this third picture, which is a pulse amplitude modulated signal. In pulse amplitude modulated signal, if you see that the tops of the pulse, follow a natural curve of this analog signal. Follow that signal. If you look at the tops of this particular PAM signal, you will find that tops will follow this analog signal, right? And naturally. So naturally, right? So that's why we call it a natural sampling. So in natural sampling, the tops of the PM signal follow the analog signal. In flat top sampling, if you look at the flat only, first we get the analog signal, then we take the samples, convert the samples to pulses. Now this time, the pulses are flat, not have a natural follow this particular analog signal. So all the tops of the pulses are flat, right? Not the curve shape as in the case of natural sampling. So in flat top sampling, the you know the tops of the PAM signal are flat rather than a curve. That's why it's called as a flat top sampling. Thank you very much.